All right, everyone. I am here with Jose Miguel Hernández Lobato, who is a university lecturer in machine learning at the University of Cambridge. Miguel, welcome to the TWiML AI podcast.
Thanks. Thanks a lot for inviting me.
Hey, I'm looking forward to digging in, learning a bit about what you're working on. But I'd love to have you start by sharing a bit about your background with our audience. How did you come to work in machine learning?
So good. That's a good question. So I was, as an undergrad, always interested in artificial intelligence. And obviously, the exposure that I had to artificial intelligence was more the traditional AI. For example, as an undergrad, I started coding my own chess programs and so on. And then when I finished my undergrad, I was deciding what to do. And there was this opportunity of doing a PhD. And at the time, the most similar thing to a PhD in AI was focused on this topic of machine learning. And I just started working in machine learning. And actually, I think I was quite lucky because I started at a time where machine learning was not so popular and so hot. And now recently it has exploded in interest and opportunities. So I think I was quite lucky to get just when it was not so popular. And now I'm in a actually very good position to take advantage of that.
That's awesome. Tell us a little bit about your research interests.
Good. So yeah, so I'm a faculty in Cambridge at the moment, and Cambridge is well known for having a strong focus on Bayesian methods. Mm-hmm. My interests are at the intersection of Bayesian methods and deep learning, and I think Bayesian methods, they bring a lot of opportunities to quantify uncertainty. And this will help us a lot to solve many problems where uncertainty is very important, especially in decision-making problems. For example, in active learning, if we want to know what data to collect next so that we learn fast about a particular problem, how to, for example, find new molecules with improved properties fast, we can also make use of this uncertainty. And even if we want to, for example, compress the parameters of neural networks so that they have a reduced size. For example, if we want to transfer a neural network to a smartphone or download it, for example, or we want to implement the neural network in hardware and we want to store the neural network in a low memory device, you can use these techniques. And in general, I'm very excited about the challenges of obtaining uncertainty estimates with deep learning. It's not straightforward, but there are many opportunities for having a big impact by doing this.
If you were to taxonomize the different approaches that folks are taking kind of at this intersection of Bayesian and deep learning, where is the activity happening right now?
Good. So what happens at the moment is that, as I said, it's not really easy to obtain accurate estimates of uncertainty. Mm-hmm. And in practice, the problem is intractable and you have to do approximations. So there are many different ways of doing these approximations. You could use, for example, sampling-based methods that draw approximate samples of a posterior distribution. You could also think of, instead of drawing samples, to come up with a deterministic approximation that quantifies your uncertainty. This will be, for example, a Gaussian distribution. You will try to obtain a Gaussian distribution that quantifies your uncertainty about the weights of your neural network. This is a different approach, and another alternative is to have something even kind of in between of the two, something more flexible than a Gaussian, but not as complicated as drawing samples. And this could be, for example, implicit models that work with very flexible distributions. So people work a bit on these different techniques to obtain uncertainty estimates. And at present, there is not really like a very well, like one method that is really known to be better than the others. And there is a lot of activity of trying to come up with methods that have good trade-offs in terms of the computational cost that it takes to obtain these uncertainty estimates and the quality of the uncertainty estimates.
Mm. And one of the areas that you've been applying this kind of work is around, in some recent papers, around molecular design.
Yeah, that's right. So that's an area that I'm really excited about. Finding new molecules with improved properties is really challenging. So usually you have to propose a new molecule and maybe you have to collect data to see how good that molecule is. And based on that data, you may update your models and propose another molecule, and the whole process repeats. And the idea is how to achieve this in a way that you find fast some molecule with good properties. So in this, yeah.
Is there a particular aspect of this problem that that lends itself to a Bayesian approach, or where these uncertainty estimates are particularly useful, or are those kind of separate areas of research for you?
So the uncertainty estimates in this case are very useful because you will use your uncertainty to guide the search for better molecules. Mm-hmm. So typically, you will want to collect data on those molecules for which you have a chance of getting good results. And this means that there should be some uncertainty or some probability that the value or the properties of the molecule are actually maybe better than what you found before. So you will use this uncertainty and actually the quality of your predictions for the properties of the molecules to decide what molecules to find next. And the molecules that you will choose are those that have some trade-off between if you think about it, the point estimate of how good the molecule is, but also some high uncertainty. And when you are able to balance these two things, like molecules where you have uncertainty and there is the probability that you will obtain actually something better than what you have found before, then you will be interested in collecting data for those molecules.
Got it. And now you've taken a couple of different approaches to this problem. One paper was focused on kind of searching over the possible chemical reactions, and then more recently, you're doing this via 3D and in 3D space. And this was a paper that was featured, or that you presented at ICLR recently.
That's right. So yeah, so the whole thing of finding new molecules is actually quite challenging because molecules are discrete objects and they have a lot of structure, and it's not really straightforward how to come up with something that looks like a realistic molecule like the ones that you find in the real world. So the approach that we follow to do this is to use deep generative models, and these are going to be deep neural networks that are trained on large amounts of existing molecules, for example, and they will be able to generate new molecules. And the question is, how do you want to represent the molecules, and how do you want to train these models to generate new molecules? So obviously, you may want to synthesize those molecules in practice. So what you could do is to have a deep generative model that is trained on existing data about chemical reactions, how existing molecules are synthesized using chemical reactions, and then you will be able to generate molecules via chemical reactions. So the model will tell you how to synthesize the generated molecules. The other approach that is also actually quite important is based on the actual location of atoms. So most generative models of molecules, they work using molecular graphs, and you will just generate a graph with the atoms that form the molecule and the connections between those. But there is a lot of important structure in the 3D configuration of the atoms that is missed by these models. And another approach is to actually generate molecules in 3D space instead of generating these molecular graphs. That is what the approach based on chemical reactions does. You can generate the molecules in 3D space, placing one atom and then connecting that atom with previous ones and so on. And the advantage of this is that you have actually more information about the structure of the molecule, and this can be very important for determining the properties of the molecule. As an example, you have that the molecule of water actually is not the way the hydrogen atoms are connected to the oxygen atom is not, for example, flat. You have like a small angle between the bonds, and this gives the molecule of water specific properties. And if you just work with graphs without taking into account, for example, this angle between the bonds, then you won't be able to capture those properties. So that's why I think capturing these properties and being able to generate molecules in 3D space is quite interesting. Yeah, so I just want to say that just to motivate this, at the moment there is a huge interest in the application of deep learning methods to this problem, because there are many opportunities to, in particular, accelerate the design of new drugs, for example. This is something that is very expensive. Companies are spending huge amounts of money into designing new drugs, and deep learning now is offering a lot of possibilities to accelerate this process.
Got it. I can see how, having worked with this data in the kind of the two-dimensional, kind of the flat graph realm, would leave you wanting to try a 3D approach. Did your specific approach, your architecture for approaching the 3D problem, did you start over, or was that kind of built on what you did for the 2D problem?
Yeah, so actually the work on 3D is one of the first works in this area. So we really were starting almost from scratch.
Okay.
And the approach is at the moment not as sophisticated as previous models, but we are able to successfully generate these molecules in 3D space. So some of the molecules that we are generating in 3D space, they are relatively simple, much simpler than the ones generated with previous models, but it's really exciting. Just to clarify how we do this, the idea is to have a reinforcement learning agent that is going to learn how to place these atoms in a space. The agent is given an initial bag of atoms, and the agent has to choose what atoms to place in a space and how to arrange those. And the only feedback that the agent gets is the final energy or the energy of the configuration of the atoms. So the agent has to learn by trial and error how to find 3D configurations of atoms that have low energy and they are physically plausible in the real world.
And so some of the traditional challenges with reinforcement learning are the sample inefficiency and the challenges of creating the objective function. How did issues like that manifest themselves in this paper?
Yeah, that's right. So typically reinforcement learning methods are data hungry. And the way we address this is to use some fast numerical methods that approximate the energy of the atoms in space. So we are actually able to collect a relatively large amount of data to find this. The problem with this is that obviously you may want to find molecules that are stable and that have like this 3D configuration that is physically plausible, but you may also want to find molecules with interesting properties. And the question is that then you have to combine these two different objectives. One is the energy of the molecule that might be cheap to obtain. And then you may also have another property of the molecule that could be actually quite expensive to obtain. You may have to do experiments in a laboratory to finally test if the properties of that molecule in the real world are the ones that you would expect. So in practice, you would have to find a balance between how to combine the two approaches. And one way to do this is to use, for example, surrogate models. The idea here is that surrogate models, these models will, for example, make predictions about the expensive properties based on some existing data. And the reinforcement learning agent will be working with the predictions of these surrogate models that will be very fast to evaluate.
And to what degree have you integrated in kind of the Bayesian approach into this reinforcement learning oriented formulation of the problem?
Good. In the reinforcement learning approach, we haven't really done that yet, but we have done that in the case of for example, the models with the chemical reactions. Mm-hmm. And the idea here is to use something called the Bayesian optimization methods. Mm-hmm. Bayesian optimization methods are actually
in the 2D world, correct?
Yeah, that's in the 2D graph setting. Mm-hmm. The idea is that Bayesian optimization methods work also by using these surrogate models, and the idea is that you will feed, for example, a predictor of the properties of the molecule that gives you estimates of uncertainty. And this could be, for example, a Gaussian process. These are very good models that work quite well to provide estimates of uncertainty. And then you can use these uncertainties to decide what data to collect next. What is super interesting is that we are using deep generative models to generate the molecules, but to connect these models with a Bayesian optimization approach, what we do is that we work with the latent representation of molecules given by the deep generative models. These deep generative models, like Variational Autoencoders, they learn a compressed representation of the data. They have some latent variables, and by using these models, we are actually able to map molecules to a low-dimensional latent space that is actually continuous. And then we can map points from this latent space back to the original space of molecules. Mm-hmm. So what we do is then use Bayesian optimization techniques to do molecule optimization in this latent space. So this is like a super interesting idea, and the advantage of this is that you have now an approach that is going to do efficient optimization, because you are using these Bayesian optimization methods that work very well in continuous spaces and relatively low dimensional. And we are combining these methods with a deep generative model that will generate molecules that are similar to those found in the real world. And this is going to be done in a way without having any expertise on how the molecules are constructed. You just have a data set of molecules, you feed your deep generative model to this data, you obtain this latent space that represents the molecules in a continuous representation, and then you can do molecular optimization in that space. Mm-hmm. So this is some areas where I'm currently working quite a lot with members of my group.
Got it. And does the surrogate model extension to the 3D setting allow you to do similar things?
Yeah, in principle, you could do similar things. This is something that we haven't really explored yet, but you could have your reinforcement learning agent optimizing some combined objective between the energy of the molecule that you are constructing and the prediction of the property of the molecule according to the surrogate model. This is obviously something that we haven't done yet, but it's a very exciting direction for future work.
Mm-hmm. Awesome. So you also do some work in compression. Tell us about that.
That's right. So this is something that is also an area where I am really excited about. And this is some work that has been done by some of my PhD students, in particular, Martin Havasi and Greg Flamik. And this is a completely radical new way of doing compression. So most compression methods, they actually work by mapping, for example, a sequence of characters to another representation of that sequence that has a size that is proportional to the log probability of the original sequence. This is what typically you do in compression, and it's well known. Not that the information that a particular value of a random variable has is determined by the log probability of this random variable. So typical methods for compression, they just compress a specific value of a random variable. They find a new representation that is more efficient. And there are many methods for doing this, like arithmetic coding is an example. What is really cool of the methods that we are working with, which we call them relative entropy coding methods, the idea is that we are not really compressing one value of a random variable. We are compressing random samples. So we just have distributions. We could have like a Bayes distribution that is shared by the sender and the receiver. And what we want to compress is a random sample from a target distribution. And we don't really care exactly about the particular sample that we get. We just want to be able to transmit a random sample from this target distribution to the receiver without actually telling the receiver what distribution we are sampling from. The receiver only has this Bayes distribution that is shared between the sender and the receiver. And yeah, we call this method relative entropy coding. And what is interesting is that this technique is able to find compressed representations of the weights of neural networks that are currently state of the art. These methods are really state of the art for compressing neural networks.
Mm. And so how does compressing the distribution lend itself to compressed communication from the sender to the receiver?
Yeah, so what you actually do is you don't really send the distribution. So you just send some bits that will allow the receiver to reconstruct a random sample. And this random sample, in general, the sender doesn't really control what sample you send. You just are able to choose randomly one and then send some bits to the receiver. And the receiver will take those bits, use the shared distribution, the Bayes distribution that is shared between the sender and the receiver, and use that Bayes distribution to recover the sample. So in general, you don't really send the distribution itself, but you're able to send samples from the distribution.
And that's because the distribution, the compressed distribution is, you consider as pre-shared. It's known to both sender and receiver.
Yes, that's right. So that's some information that is agreed between sender and receiver. And typically, this could be a very simple distribution that is easy to sample from. For example, a standard Gaussian distribution. And what is interesting of this method is that you are really just sending random values of random variables without caring much about the value of those. And this is extremely useful for compressing the weights of neural networks, because neural networks are very, very tolerant to perturbation of the weights. So it might be fine if you just send some randomly corrupted version of your weights. Your neural network might still be able to make accurate predictions using that corrupted version of the weights. So by doing that, by sending some small perturbation of the weights and not exactly caring about sending a specific value of the weights, we are able to achieve the best existing compression rates for neural networks.
Got it. But you might not want to apply this to traditional communication.
That's right. So the question is, what type of communication you can apply this to?
Yeah.
It turns out that you can actually apply this to many other types of data, not only the weights of neural networks. For example, images. You may say, I want to send some image. You may also tolerate some error in your image. And it turns out that it might be fine if you send just some version of your image that is slightly corrupted. This is usually called lossy compression. So you won't be able to send the original image, but the reconstruction quality of the image could be still quite good. And obviously, all this depends on the trade-off that you have between how much you want to compress the image, and you would have a potential loss, and maybe you don't want to compress the image so much, and the loss is not so high.
And then you've also been applying deep generative models to robust prediction. Tell us about that work.
That's right. So this is something that we have been really working on very recently, and there is a lot of interest in this area. So it turns out, I mean, this is widely known. Deep learning methods, they are not very robust, especially to spurious features, for example, that could be looking as useful to make predictions in your data, but they're actually not like this. And the typical example of this is this problem where you have to classify images of camels and images of cows. And you could imagine that the cows appear typically with a background of a green field, and the camels could appear with a background of a desert. And if you try to feed a deep learning method to classify these images, the deep learning method is very likely to fix on the background pixels, which are not really representative of what you want to learn. It's not really differentiating between the shape of the cow and the camel. And when you try to make predictions, then, for example, for a cow that is standing in a beach and not in a green field, then it's going to make horrible mistakes. So the idea is then, how can you make deep learning methods more robust so that they don't fix on these patterns in the data that are just spurious and they are not really representative of the prediction problem that you want to solve. So there has been a lot of interesting work in this area, especially with some methods called invariant risk minimization. And they actually come up with solutions to this problem, but they are based on using linear models. And obviously, linear models, they are not really going to be very accurate in many different settings where actually the patterns in the data are not linear. So what we propose...
Let's start with invariant risk minimization as a
that's
broad
right.
concept.
So this is the work on... that's right. You know about this work. It's very widely known, and it's had like a lot of impact. So
well, I was going to ask that you explain that as a broad concept, independent of linear versus nonlinear.
Yeah, so the idea is that you want to find some, the idea here to solve this problem is to find some predictor that is going to be invariant across different representations of the data or environments. So that, for example, you could imagine that you have these images of camels and cows, and the type of background maybe changes slightly across two different versions of your data set. And then what happens is that these correlations between the background pixels and the target label is going to change from one version of the data and the other. Maybe in one version of the data, the fraction of the cows with green fields is slightly higher than in another version of the data. So if you have a predictor that focuses on these pixels, then it's going to be changing across these environments. So in some environments, the predictor could be more reliable, and in other environment, it might be less reliable. And this allows you to identify that the patterns that the predictor is capturing are probably not realistic and spurious. So the idea is to find some predictor that will be invariant and is going to work well across different environments. And for example, this predictor that focuses on the shape of the cow or the camel will be invariant. And the idea is to have a predictor that, for example, could work in the nonlinear case. So I can say briefly how we solve this problem. Yeah. And the idea is that we use deep generative models also to solve this problem. And we use something really cool and that is really exciting at the moment. And it's a family of deep generative models of variational autoencoders that are identifiable. This is well known that existing variational autoencoder models, if you feed them to the data latent variables that you will be obtaining could be different if you train different times your methods. So there are many different transformations of your latent variables, and the model could just learn to achieve those transformations. So in general, every time you learn your model, the latent variables that you could obtain encoding the data could be different. And this makes these methods not very reliable if you want to use the latent variables for predictions. What has been very recently developed is a family of deep generative models or variational autoencoder models that are identifiable. And this means that every time you train these models on the data, using, for example, different initializations of your neural networks, you will always obtain the same latent variables. And actually, this can be useful for solving this invariant risk minimization problem. The idea is that you will find latent variables that represent the data, and then you can use causal identification methods to choose those latent variables that are actually predictive of the target property. So in the case of the images and of camels and cows, you could think of fitting an identifiable variational autoencoder model to this data, and then finding some latent variables that some will be describing the grass and other variables will be describing the shape of the cows and the camels. And using the causal identification methods, you can choose those latent variables that are actually connected with the shape of the cows and the camels with the final label. And the other latent variables like the green fields and that determine the green field or the desert, they won't be captured and they won't be identified as causally related to the target label.
Can you give us an overview of how the causal identification part of that works?
That's right. So what happens is that you have an underlying causal models. So you have these latent variables that you have learned with the identifiable variation autoencoder model, and you have now data for the values of the latent variables and data for the target property. And obviously, you also have data for the different environments that I mentioned before. All this works only if you have these different environments where things change. So once you have observations from these latent variables, you can try to identify what's the actual causal direction in the generation of the data. If, for example, the latent variable points towards the label, and that means that the label is actually generated by the latent variable, or actually the label for the image points towards the latent variable. And that means that actually the latent variable is caused by the label. So the causal identification methods, they will apply either independence tests to identify what is this right direction for the arrows that connect the different variables, or they are based on other underlying assumptions. Like, for example, something that is used in practice is to assume that the label is obtained as a nonlinear transformation of the latent variable plus some additive noise. And if you have a model that works in that way, you have that the label is actually generated as a nonlinear transformation of the latent variable plus some noise. You can actually identify the right direction by just fitting the nonlinear model in both directions. You can try to use a nonlinear model to predict the label from the latent variable, or a nonlinear model to predict the latent variable from the label. And you can then look at the statistical patterns in the noise, and the right direction will actually have specific properties that allows you to identify that. This is some work on causal inference that has been really exciting. This was done in Bernard Cherkov's lab. And this work actually that we're working on this, and we plan to submit it to NeurIPS. This is done also in collaboration with Bernard Cherkov and one of my PhD students.
Got it. And so how, in the case of this last work that we've been discussing, how do you evaluate the results and how well is it working?
Good. So yeah, so right now evaluating the performance of these methods is challenging. And right now there is a benchmark problem that people are considering for the evaluation of these methods. And this is called the colored MNIST. It's a, MNIST, everyone is familiar with MNIST, everyone that works in deep learning. So you have the MNIST, this data set with digits, and you will have that some digits have different colors. So you color the digits with the colors are red or green, and you will choose these colors in a way that they are spurially correlated with the target label. So you will have some of these fake correlations between the colors and the target label. And obviously, for example, you could say, you typically classify the digits in two categories. I think from 0 to 4 is category 1, and from 5 to 9 is category 2. So you will say the color of the digit most of the times agrees with the actual category. So you have these colors that are correlated with the label. And what happens is that you have two different versions of your data where this probability of agreement of the color with the label changes slightly. And this is related to this thing that I mentioned before, that you need some variation in the spurious correlations to be able to identify them as spurious. So you can then train deep learning methods on this data, and what happens is that the test data, actually the color has no association at all with the label. So actually, if you train a deep learning method on this data, and then you evaluate the predictive performance on the test data, a normal deep learning method is going to perform extremely poorly because the colors are actually the opposite. The correlation of the colors is the opposite at test time. So you could use this benchmark to see how well you are doing. And actually, we have extremely good results in this benchmark because we are able to both find nonlinear representations of the data and also nonlinear predictions. We are able to do nonlinear predictions with the methods that we have developed. We achieve some of the best existing results in this particular benchmark.
Awesome. And talk a little bit about how your broader work around applying Bayesian methods and uncertainty estimation applies in this particular problem.
That's right. So in this case, the idea is the variational autoencoder model. So we have this latent variable model that explains how the data is generated. And obviously, you have latent variables. So these are variables that are not really observed. So the deep generative model uses these latent variables to generate the data, but you don't observe those. So you really need to infer those latent variables from the data. And you need to use Bayesian methods for this. For example, you have to do something called typically variational inference, where you feed a simple approximate distribution to the posterior distribution over the latent variables. So you could use variational inference to solve this problem. However, it's much better if you use other techniques. And this is what I mentioned before about the different trade-offs that you have in Bayesian methods. That you could have simple methods that are maybe computationally cheap and they work relatively well, but you could have more advanced methods that are maybe more expensive, but they can be much more accurate. And an example in this case could be sampling-based methods. You could think of, instead of using variational inference, which is what most people use when they train variational autoencoders, you could use some sampling-based method to do something more efficient and more accurate in this case.
Awesome. You've got a few other papers at this latest iClear conference.
Yeah.
Why don't we quickly kind of talk through those? One of them is
so I can
uncertainty.
Yeah, so I can talk a bit about some of those papers as well. There is also another paper which I'm also really excited about, and it got an oral presentation at iClear, and it's called CLUE, and it's a method for interpretability in machine learning. Right now, there is a lot of interest in trying to open the black box of deep learning methods. No, you train these methods and you don't really know why they make some predictions. So a lot of people have been focusing on interpretability methods for normal deep learning techniques. And they will say, oh, my deep learning method now says that my loan should be rejected, for example. And you're interested in knowing why that happens. However, as I mentioned before, uncertainty is very important in many decision-making problems and in many prediction tasks. And if you care about uncertainty, you may have that your Bayesian deep learning method just tells you, I don't really know what's the prediction, what's the prediction in this particular setting. For this particular data point, maybe I don't really know if you should be given your loan or not. So I'm very uncertain about what the right prediction should be. Yeah. And the question is then, why is your Bayesian deep learning method uncertain? You may want to actually try to understand what's maybe making in the data your deep learning method uncertain. Right.
So conventional explainability is focused on the prediction, and in this CLUE paper, you're focused on the uncertainty estimate.
That's right. We are actually focusing on interpreting uncertainty estimates and trying to come up with interpretability of why deep learning methods might be uncertain. And what is interesting is that we also use deep generative models and variational autoencoder models for this.
Okay.
So the idea is that
things.
yeah, it's similar techniques, and obviously there are many applications of these methods.
Sure.
So what we do is we say, okay, we have this Bayesian deep learning method, and it's saying that this particular data point is highly uncertain. So what we do is we train a deep generative model, a variation autoencoder model on the data, and this will map the data into some low-dimensional latent space. And now what you can do is try to find new points in this latent space that are close to the original data point, but where the uncertainty of the neural network, when you decode those latent points back and you make predictions, the neural network becomes more confident. So by doing this, we are now able to say, you have this data point for which your neural network is very uncertain. Now I have this other data point that is very close to the original one, but the neural network is much more confident and it's much more certain. And now you can look at the two data points, the one for which the neural network is uncertain and the one for which the neural network now is confident. And this will give you a lot of information telling you why the neural network is uncertain. You can look at the differences between the two data points, and you will be able to understand why this is the case. And we have tested this on, obviously, MNIST. We have these MNIST digits, and we get some of these digits. We have, for example, a 4 looks like a 9, but you wouldn't really be able to say this is a 4 or this is a 9. And then this method precisely tells you the pixels in the image that are actually creating the confusion in the Bayesian deep learning method. It's highlighting, for example, those pixels that make the 4 look like a 9 or not. And I'm really excited about this because I think it's opening now a new area for research in interpretability, because people will now think, okay, now we can apply interpretability methods to uncertainties, and we can try to understand better why our methods don't know what they should know.
So you're help me understand how the approach helps you interpret what's happening. So you are finding close points in the latent space, and we understand kind of some geometric properties about the relationships between points in the latent space, but we don't necessarily understand the latent space itself and kind of what the dimensions, in that space mean. So how does knowing, how do you get from kind of knowing that two close points share similar values? How do you get from there to understanding the causes or being able to interpret?
Yeah, so that's a good question. So why this whole thing works, and how just operating in this latent space makes any sense. So the idea is that the latent space, the way you train these models is that the latent space has some structure, and it captures some similarity between the different data points. So because the latent space has low dimension, you will have to find some compressed representation of data points in this latent space. And whenever two data points are close to each other in the latent space, they should still exhibit some similar patterns or regularities. Otherwise, you wouldn't be able to compress the data. So we know that now data points in latent space that are close to each other should be relatively similar. So our goal is to find these different versions of the original data point for which the neural network is more confident, the uncertainty is less. So what we can do is now map these points from latent space into the predictions of our model by just decoding from the latent space, feeding that as an input to the Bayesian neural network, and then getting the value of the uncertainty. And then you could just do gradient-based optimization in the latent space to find some new point in the latent space that decodes into something that the neural network is highly, much more confident. And obviously, you want to stay close to the original point, because otherwise what you could get could be very different, and that would be not very informative. No, if you just say, oh, this is a data point where you are very confident, and the other one where you're very uncertain, and they are completely different. You don't really find anything, any pattern there that you could that could explain why things happen. So this technique is actually called the counterfactual. It's a counterfactual method for interpretability. And what typically means is that you say, I have this data point, and actually my predictions are very uncertain. And by using this counterfactual approach, you say how my data point should have been so that my network is very confident in your predictions. That's what we are trying to do, a counterfactual, by saying, okay, this is the data point that I got. Now imagine that things would have been otherwise, and I got another version of this data point for which my neural network is much more confident. And then by just sticking to something that is close in latent space, but where the uncertainty actually decreases quite quickly, then we are able to obtain these informative data points.
Got it. Awesome. Well, Miguel, thanks so much for joining us and sharing a bit about what you're up to.
Thanks a lot. Yeah, thanks a lot for inviting me.
Awesome. Thank you.